we talk about we get barrels of petroleum from the ground. How many barrels of petroleum are we pumping out of the oil rig, out in the Gulf Coast and whatnot. And so what end product do you get? Now we know that the petroleum is a liquid mixture, then what is the end use product of those components in that liquid mixture? Well, most of it in this mixture, most of it is going to be used in the form of gasoline. So most of the petroleum is separated and modified and used as gasoline. The next largest fraction is diesel fuel for big trucks and also home heating oil. Then the next little bit is jet fuel, and then heavy fuel oil, LRG, liquefied refinery gas. That would be, for example, propane. It's liquefied and transported, and you see these large propane tanks outside of people's houses that aren't hooked up to a natural gas line, and that's actually the gas that they use to heat their home. Or also propane you use for your gas grill. That's the liquefied refinery gas. And then other products, 7.6 gallons. And other products include, which we'll talk about more next semester, but a lot of the starting materials for plastics come from petroleum. And so here are other products. This is not used for energy. These are all energy uses. And then actually the material that is in plastics, the starting material that is then synthesized in chemical companies comes from petroleum. A lot of pharmaceuticals, the starting material to make pharmaceuticals comes from petroleum as well. So all of this is just burned away, and then this is used for the materials that we know of in our modern plastic society. Okay, so how do we manipulate these molecules? There's this situation here where we show that, since we use so much for gasoline, the fraction is not mostly gasoline that comes off. It's this pretty much equal mixture. So actually, out of the petroleum, we need mostly gasoline. That's the bottom line. So what happens is then we get these heavier fractions, and we crack them to make them smaller so that we can formulate them into gasoline. Okay, so some of the heavier molecules, they're not really useful. We don't need that much jet fuel or diesel fuel. We need more gasoline. And so they take this at the refinery and they subject it to some chemical change, which we call cracking in a cracker, and it's reformulated into smaller molecules that can be used for gasoline, because that's our biggest need. So in that cracking, there's two different types of cracking. There's thermal cracking and there's chemical cracking. And literally what it means is that the thermal is just high heat, subject this larger hydrocarbon. In this case, this example is C16H34, which is too big for gasoline. You can subject it to high heat, and it will crack. It will break into two smaller molecules. For example, H22 plus C5H12, and you see that the total number of carbons, this is an H here, the total number of carbons is conserved, the total number of hydrogens is conserved, is just broken, and when you conserve it that way, you end up forming one double bond. That's why there's a crimp here in this particular space filling model. There's a double bond here between these two carbons, and it causes it to bend like that. You lose your tetrahedral and you go into a trigonal planar type shape when you end up with a double bond, and so around those two carbons. Anyway, thermal cracking is a bit expensive. It's energy expensive. It takes a lot more energy to get the temperature up, so you're using energy to do it this way. So a better way of breaking these molecules is called chemical cracking, and in this way they take advantage of a catalyst. Okay, so catalysts have been developed. It's a big industry to figure out more energy efficient ways of reformulating the bigger molecules into more useful gasoline-sized molecules. And so the thermal cracking is when you use heat. Chemical cracking is when you do it using a catalyst. So it's a big business. Different companies own patents for the different catalysts and whatnot to try to make their gasoline cheaper so they can make more money. Finally, a third type of manipulating the molecules that are in the petroleum is something called catalytic combination. and that is taking those the gases that are not terribly useful, the methane, ethane, propane, and butane, they called the liquefied refinery gases, separating those off and combining them using a catalyst to make the bigger more useful. Here's, whoops, that's a strange thing to do. Here's an example. It is C2H4. That's ethylene. That's got a little double bond in it. That might be a gas that's found. It might be too small of a piece that came from the thermal cracking, the chemical cracking, or it might be a molecule that was mixed in with as one of the pure substances within that big mess that we call petroleum. And this is catalytic combination. In the presence of a catalyst, they'll take some of the smaller ones, make them bigger, C8H18, that's octane. Okay, so this is in the range of gasoline size, this is gasoline size, and this is gasoline size. So there's all different things going on at those refineries. The one big thing they do is they separate the petroleum liquid mixture into different fractions. Then they take those fractions and make them into more marketable size molecules, the smaller ones combining to make gasoline size, the bigger ones cracking to make gasoline size, because that's the most demand. That's the type that's the most demand right now. Another thing that happens under the reformulation at the refineries, the cracker is where we're making them making them smaller. The reformer, we could be in this process, this is just a schematic diagram, so there's a process that's going on at some part in the plant, and there's a process going on at a different part of the refinery plant where we reform. And in that thing, there's two things that can be going on in the reformulation. One is taking the molecules that are of the right size, wrong one, this one up here. Taking the molecules that are of the right size, this is octane, and rearranging it into a more useful arrangement. This is also a form of octane because there's 8 carbons here, 1, 2, 3, 4, 5, 6, 7, 8, and there's 8 here. It's just all in a straight chain. And as it turns out, the way the hydrocarbon is arranged makes it a better fuel or not so good of a fuel. When the octane is arranged like this, it's just called N-octane, normal octane, and in this case it's called isooctane, an isomer of octane. And as it turns out, this is how we get thousands and thousands of different hydrocarbons. There's a limited number of arrangements, C8H18, C7H16 and whatnot, but then the way they're individually put together, each different combination is considered a different isomer. Even though it has the same molecular formula, it has a different structural formula. So these both have the same molecular formula, but they have different structural formulas. And because they have different structural formulas, they have different chemical and physical properties. And as it turns out, when octane is arranged this way, in the form of isooctane, it burns better in a combustion engine, less knocking. Okay, so it just burns slower. It's harder for the oxygen to get to all the carbons when they're bunched up like that than when they're in a chain. So it's a slower burning type of a fuel, which in the car engine, an automobile engine, happens to be a better way. So one of the things that goes on at the oil refinery is this reformulation, taking the certain isomers and undergoing some chemical change to rearrange them into a formulation or into a form that is more useful for the market. And the big market is the gasoline market. Okay, and so this is actually based on this concept is how we get the octane rating. You know, when you go buy a gasoline, gas has an octane rating. It's either going to be like 87, 89, 92, something like that. And they're more expensive because more effort has to be put into the higher octane rating. But where the octane rating comes from is comparing the knocking, the amount of knocking that occurs with N-heptane, which is just a straight change C7H16, versus 100% isooctane. So isooctane is the best 100%. Of course, that would be too expensive for everybody just to have 100% isooctane. So there's always some combination of hydrocarbons that when the way they perform is an octane rating of around 87, and so that would be a mixture of 87% isooctane and 13% heptane. and that's how you'd get your octane rating, the number of knocks per minute, or however they quantify it. So anyway, another thing that helps with the octane rating is methanol, ethanol, and methyl tertiary butyl ether. These are oxygenated compounds. Adding the oxygenated compound and having as much like isooctane type compounds in your liquid mixture that is petroleum will give you the best type of octane rating. So adding these is even better than isooctane. So if you've got a little bit extra of the molecules that behave like heptane and you add some ethanol, you're going to improve your octane rating, you're going to improve the efficiency of your engine, and you're going to reduce the knocking, which is when it burns too fast and expands too fast, the gas in your combustion engine. Okay, so so that's the octane rating. It's going to have some oxygenated additives. It's going to have some ratio of hydrocarbons that's going to be compared to the ratio of 87% isooctane rest heptane versus 89% versus 92% isooctane on the rating scale. And then these oxygenated compounds, really ethanol and methanol, or methyl tertiary butyl ether, are more common than methanol. But when we see reformulated gasoline, what's happened is at the refinery is the hydrocarbons that were originally separated from petroleum have been rearranged to give in the right hydrocarbon size, and then they've been manipulated to have less of the straight chain, more of the isomers where they're more bunched up, and then also you've added these oxygenated additives. And also you removed some of the more carcinogenic petroleum products. Okay, so there's a lot of gasoline a lot has happened to that petroleum product to make the gasoline. This is ethanol, this is methyl tertiary butyl ether. The important thing in both of these is that oxygen is now in the mixture, and having oxygen mixed in with the liquid helps it burn more efficiently, because you're not just relying on the oxygen of the air that's mixed in, but also you've actually got some oxygen mixed in with that liquid mixture. Now the problem with adding into the fuel, I mean obviously the hydrocarbon part of it will burn, but by adding the oxygen mixed into the fuel, you get less energy per total gram of your gasoline when you add these oxygenated additives. So it's a kind of a catch-22. You're getting less energy out, but it's a cleaner burning fuel because there's more oxygen. You get less carbon monoxide. You've removed some of the carcinogenic petroleum products and whatnot. So that's what goes into making gasoline. It's quite a process, but it's been well done. Now there's some, you can read about the, and we'll talk a little bit more about the issues around ethanol, since a lot of it's made from corn, and corn could be used to feed hungry people around the world. There's a bit of an ethical issue of using ethanol. And then also the methyl tertiary butyl ether was a great oxygenated additive, but as it turns out, it is a carcinogenic itself, and it gets into the groundwater from being so much in the environment. It pools in the groundwater, and there's actually this particular additive has been banned in California, and it'll probably eventually be banned completely, and we'll be back to using ethanol, or maybe somebody will come up with some better oxygenated compound that doesn't take away from the food supply and doesn't pollute the groundwater.